Models are really important in science. So what you have to understand is that they're key to the scientific method. There's a difference between reality and creating a model. So model is the thing that we play around with in science, and we create models based on the data we collected. Now, almost everything in science is a model. So when you read Plato or you listen to Plato's Republic, he gives the allegory of the cave. So he's saying that whenever we rationalize anything or come up with any kind of model or understanding or prediction about the future, we are just seeing a shadow of what the real world exists. And it's just scattered on the back of our cave. We never get to see the true light of reality. So I was once demonstrating protein structure, and I'd drawn up a nice ray traced image a bit like this one, and someone came to me and asked me, what colour are proteins? But it makes no sense whatsoever. Proteins can't have a colour because they exist at such a small scale that light cannot bounce off them. They're the wrong wavelength, so they can't have colour. We just use colour when we're drawing these things, and even the ribbon diagrams, to try and simplify how proteins appear to make it easier for us to understand. If I show where all the atoms are, it just looks like a big ball of knitting. In fact, it looks like a dense blob. If I was to then go to the next level of understanding and think about where the electrons are, it would look like a very fuzzy blob. Now, with a model, you have to think exactly what do you want? What are you going to use it for, and what aspects of it are important? How reliable do you need it to be? It's perfectly fine to have this plum pudding positive and negative view of the atom. It doesn't damage your understanding for you to know that there are charged particles inside it. Bohr changed his model of the atom to have much more empty space and the nucleus and the electrons going around it once they found that alpha particles pass through gold nuclei. This is important for the aspects that they are trying to illustrate in that particular point and that particular model. But if you just treat the atoms as hard spheres, there's nothing wrong with that model if you don't care about the subatomic structure. Here is a model of a Formula 1 car going through an air turbulence simulation. This is a computer model of it. But when you build a miniature model, you have to take into account lots of different effects because of scale. So if you imagine your model is a tenth the size, that means all of the air molecules that are hitting it are now 10 times bigger than they are against a real sized car. So this means you have changes in viscosity of flow of the air over the model of the car compared to how it will flow over the full size car. And you have to take these effects into account, which you can do through computer models and modifications of your simulation. But you have to know what the limitations of your models are. How do you create models? Well, usually models begin from some kind of anecdote or observation. So a guy called Ignaz Semmelweis, who we've encountered before, or hopefully you've encountered before, he saw that more women were dying from childbed fever in wards attended by doctors rather than midwives. So he was trying to figure out, what do doctors do that midwives don't? Well, doctors do a lot of dissection and dealing with cadavers. And he therefore concluded that it was transfer of material from the cadavers that was causing the problem, and it was causing childbed fever. This was before we realised about infection and disease. So he said, by getting the doctors to wash their hands in chlorinated lime, which is not going to be nice, this will remove the material that's causing this problem and therefore save lives. It did, but he could never fully convince the medical community. And that drove him mad, because he could see that his idea was going to save lives and people were not acting on his ideas. So people were dying that he thought he could save. And that eventually led to him having a nervous breakdown. He was institutionalized, and he died 14 days later because of being manhandled in the institution. You don't have to create a model based on some physical attribute. You can also do things like maps are a very useful way of creating models. So this is a classic epidemiological map created by John Snow of the deaths around the Broad Street pump. So the closer you were to the pump, the more people who died. So each one of those black bars represents a coffin and represents someone who's died. So he concluded that this cholera outbreak, which was causing all these deaths, was because of contaminated water at the Broad Street pump. Then, supposedly, he took the pump handle off and the outbreak stopped. Now, unfortunately, outbreaks actually stop on their own because, as we're going to find out with COVID, because eventually they pass through the entire population and you've either died or recovered and become immune. But this was a useful model to help us understand how cholera was spread. So the general model of epidemiology looks at associations. It looks at people who are exposed to something or treated to something or not treated, people who are not exposed. Then it looks at the outcome. Are they affected or not affected? The classic example of this is lung cancer and smoking, but also asbestos and certain types of cancer were discovered using this epidemiological model approach, where you see more people are affected in the exposed group and a lot less people are affected, so you have more non-affected in the not exposed group. Again, that's another model, this time represented as a table rather than as a map. And another way you've used models is standard curves and calibration plots. These are models about how a variable in X is related to a variable in Y. And you use these all the time in calibrations of running things on gels and other calibration curves. They're always models.